Hi, today we're presenting about discrete element method. Our team members are Abdul Hamid, Imad, Kiroi, Mohammed, Segan, and Zin Shin. In this presentation, we will be going over the historical background of DEM, followed by general principles, governing equations, and some hand calculation examples, in addition to numerical examples and some applications this method can be useful in. The discrete element method, or DEM, is a numerical approach that models systems made up of discrete particles. It was first developed by Condell and Strack in 1979 to use it for rock mechanics simulations. In DEM, each particle is treated as an independent body with its own position, velocity, and rotation. These particles interact with their neighbors through contact forces, which are calculated explicitly using physical laws. The image shown is a group of spherical particles representing a material like soil or powder. We have zoomed into the interaction between two particles to illustrate the contact force model. This mechanical analog, consisting of springs, dampers, and sliders, represents the physics of normal and tangential interactions. The spring captures elastic deformation, the dashpot models energy dissipation, and the fractional slider stimulates resistance due to contact. This setup allows DEM to replicate real material behavior at particle scale. It's widely used in geomechanics, powder compaction, and fracture propagation problems, where understanding contact mechanics is essential. This table provides a concise comparison between continuum-based numerical methods such as FEM, SPH, and discrete approaches like the discrete element method. Continuum methods operate under the assumption that material is smoothly distributed in space. Quantities like stress and strain are treated as continuous fields and are governed by partial differential equations. FEM is widely used in structural and mechanical applications to simulate elastic and plastic deformation, while SPH, a fresh mesh technique, is effective in fluid dynamics and large deformation problems. In contrast, DEM treats materials as collection of distinct particles. Each particle has its own mass, position, and velocity. Additionally, these particles obey Newton's second law of motion. The method explicitly calculates contact forces, whether they are normal or tangential, between each individual particle using force displacement laws, such as the Hertz-Mendelian model or Coulomb friction. This fundamental difference in modeling approach also determines where each method is most effective. Continuum models are best suited for materials where the deformation is smooth and the microstructure can be averaged. DEM, however, is preferred when the microstructure plays a dominant role, such as in granular media, particulate flow, fracture propaganda, and powder compaction, where particle-level resolution is necessary. The trade-off is computational. DEM is more demanding, especially for large-scale or high-resolution simulations, due to the explicit time integration and contact calculation for every particle pair. In short, the choice between continuum and discrete modeling is not just about the problem size, but about the underlying physics. When particle interactions, discontinuities, and contact dynamics are dominant, DEM offers a physical, realistic, and insightful alternative. One of DEM's greatest strengths is its ability to simulate particle-scale interactions explicitly. Each particle is treated as an independent body governed by Newton's law, contact forces, damping, and sometimes cohesive, that are calculated directly. This makes DEM highly effective for problems involving granular flow, solid behavior, powder compaction, and rock breakage. Additionally, DEM excels at modeling discontinuities. While continuum models struggle with crack propagation or localized failure, DEM naturally resolves these through the mechanics of individual particle interactions. It can simulate complex phenomena like jamming, particle segregation, and structural collapse at high spatial and temporal resolution. However, these capabilities come with significant computational costs. Since the DEM typically uses explicit time-stepping and resolves every contact at each time increment, simulations can be extremely expensive, especially for systems with thousands or millions of particles. The time step is constrained by the material stiffness and mass, often in the microsecond range. Another challenge is calibration. While the force models in DEM are physics-based, their parameters like stiffness, damping, and friction must often be tuned or measured experimentally. This makes modeling difficult without experimental validation or sensitivity analysis. Finally, DEM is not well suited for systems where the material behavior is mostly continuous or dominated by global deformation. In such cases, continuum methods like FEM are much more efficient, especially for stress analysis, heat conduction, or structural stability.
Okay, now I will talk about the historical background of the DEM. In this first slide, in the top corner, you can see the picture of Dr. Peter Candle. He is the person who developed the DEM method. Many people call him the founder of DEM. His idea helps scientists and engineers model how materials like rock or particle move. We will now go through the history of DEM year by year, starting from the very beginning. In 1687, Newton published his famous book called Principia Mathematics. In this book, he introduced the laws of motion, like how objects move and stop and speed up. These same laws are still used today in DEM to calculate how particles interact and move around. In 1956, two scientists named Alden and Winter Wright began simulating the movement of atoms and particles using computers. This was called molecular dynamics. It was the first step toward modeling materials using individual particles. In 1970, Peter Candle and Otto Strack came up with a new idea. Instead of modeling materials as a one solid object, they thought about modeling them as many small blocks that touch and slide and push each other. This was the first concept of DEM. In 1971, Candle used this method to study how rocks move in a slope. This was one of the first time DEM was used in a real engineering problem. He used it to understand how landslides happen and how to prevent them. In 1974, Candle created one of the first DEM computer model. He used it to simulate tunnel support and how rock would behave under stress. In 1977, a researcher from Japan named Kawa used DEM idea in structural engineering. He showed that DEM could also be used in a building design and problem solving in construction. Then in 1979, Candle and Strack published the first full scientific paper about DEM. This paper gave a scientist a full framework to simulate particle and become a key reference in engineering research. Now I will move on the second slide. Also, the second slide, in the top corner, you can see an image from a 3D DEM simulation. Each small ball in the image is a particle, and the color show how they move during the simulation. These type of models are now used in a field like energy. The second timeline covers the next stage of DEM development from 1980 to 1992. In 1980, a program called UDEC was released. This software allowed engineering to use DEM in 2D to study how rock fracture form. In 1983, more advanced tools were introduced to model rock with a joint that move and break. These tools helped expand DEM into a real-world engineering project. In 1985, a new method called DDA, which is discontinuous deformation analysis, was introduced by Shi. DDA is a little different from DEM, but it also studies how blocks move and rotate. In 1988, a researcher named Gilbert created the first version of 3D DEM. This allowed engineering to simulate a block motion in 3 dimensions, which was a big improvement in the DEM. In 1989, research like Williams and Banda used DEM to study a real rock structure. Their work provided that DEM could be used outside the lab in actual construction and geotechnical projects. In 1990, a program called Trouble was created. It helped model how granular materials like sand, grains, or powder move in soil or harbor. And finally, in 1992, she completed the DDA method. This version became a trust simulation tool for engineering, studying how rock or block deform and shift. So, in total, this timeline shows how DEM starts from the Newton's law in 1687 and grow into a full simulation tool by 1992. The work of Dr. Peter Candle and many other research helped make DEM a valuable method used in many industries today. Thank you, and now I will pass it over to my colleague who will continue with the next part of the presentation.
The core principle behind the discrete element method is the application of Newton's law of motion, both transitional and rotational, to each individual particle in the system. This means DEM tracks not just the position and velocity, but also angular motion and torque for every particle. To determine how particles interact, DEM uses force displacement models. For normal forces, it often applies Hertzian contact theory, which describes how elastic repulsion arises when particles overlap. Tangential forces are typically modeled using Coulomb's friction law. Damping and stiffness terms are included to realistically account for energy dissipation and contact duration. Efficiency is a major consideration in DEM. especially in systems with large numbers of particles. That's why contact detection relies on neighbor lists or spatial partitioning, like cell-based grids or varlet lists, to quickly identify which particles are close enough to interact. These calculations are embedded within a simulation loop. At each step, the DEM engine detects contacts, computes interaction forces, applies Newton's law to each particle, updates motion, and repeats. This loop enables DEM to capture complex behaviors such as granular rearrangement, jamming, particle breakage, and contact evolution, phenomena that continuum models often fail to resolve.
Okay, let me explain this in a simple way. In DEM, we have two ways to model how particles touch and move: hard spring and soft spring. The hard spring model is pretty basic. Particles just bounce off each other like spinning balls. There's no overlap, no real contact first, it's just one collision at a time. So it's fast, but kind of too ideal. Now the soft spring model is more advanced and more realistic. It still treats particle and rigid, but it allows a little bit of overlap. That small overlap is used to calculate the article force between the particles. This includes normal forces, tangent forces, and even no contact forces like gravity or cohesion. Plus, particles can have many contacts happening at the same time, which is way closer to real material like powder or sand. That's why in most DEM simulation, especially in engineering, people prefer the soft-spring model. It's slower, but it's given much more accurate result. DEM is basically a visual drawing of green. The computer keeps track of where every grain goes and how it spins, using nothing fancy than the Newton's laws. All we really need to watch are two things: how the green sails through space and how it's spinning about its center. Next, each time steps the code just add up the pushes and the twists, update the motions, and repeat. String those steps together, and we can see poke behavior like mixing, poking, or flow. Okay, this picture shows how DEM moves one grain. Push from other grains. When two grains touch, and they push each other. Tiny per cause a gap. Even if they don't touch, they can be a small attraction. Air or water drag. The floor around the grain slows it down. Gravity, always pulling it down. We add those four forces together, then use the basic Roy's force equal mass time acceleration. That's just Newton's law. The computer does this every tiny time step for all the grains, so they are spent and the position kept updating. After many steps, we can see the wall poke flow. This force list is based on the classical DEM paper by Zhou et al. 2007. Alright, last bit, rotation. On the right, you can see the same three grains, but now I'm focusing on spinning instead of sliding. The rule is just Newton's law for rotation, Tokyo equal inertial time, angular acceleration equal IR. Where does the torque come from? The contact first isn't hitting the center. It heads off to the side, so it tries to test the grain. The same goes for any pull across the gap or dragging for the fluid. We add up all these later testing effects that give us the net torque. Then the computer updates the spin rate of every tiny stem step. Put together with the sliding equation from last slide, This covers all the way the particle can move. On the last side, I just list the extra focus beside the occlusion. Friction slows the particle when they slide. Plasticity rebound, they squash a bit and spring back. Gravity, everything pulls downward. Cohesion and adhesion, like the white stand that stick together. Molecular forces, for tiny particle, electricity or van der Waals. The particle on the right is a lateral spring. When two particle press, it's like screens or spring. The screen density is X. The stiffness is K. The first is F managed Kx. DEM just add up all these first each time step to get the next position. That's it. We are simulating electric charges and how they move over time. First, we calculate the first and get the conclusions of each particle. Then we use numerical integration to update their velocity and position. The method we use is called the explicit Euler method. It's a simple way to update motion step by step. We start from the current position xt and the velocity vt. Then we use the vt to get the next position xt per double t. At the same time, we use the conclusions ETs to update the velocity to vt to double t. Here, double t means nice multi-time step. During each step, we assume the velocity doesn't change. In this diagram, the green bar shows the position of the particle at each time step. The blue arrow as the velocity as the dashed line shows the moment. This example only shows translation, but the same method can be used for rotation too. Overall, this method is easy and useful. It's used in many physics simulations like DEM.
Now, I am going to discuss the AND calculation, and the example I'll be looking at is two colliding steel balls. So we can see that for two scenarios, scenario A and scenario B, we have two balls of mass M1 and M2, and we see their position before contact, at contact, and after contact. The scenario A has at the contact has the balls M1 and M2 like overlapping a bit at the point of contact, and that's the soft sphere model that it has lasting contact. And the scenario B has like they're just meeting for a very short time, and then they are rebounding, like they're going in different directions, elastic collision afterwards. So like that's that for like soft sphere model and hard sphere. Over here we have the schematic for two colliding balls at the instant where the two balls actually make contact with each other. So there are so many other modifications, but like these are the like two primary models, contact models that we use in like the DEM simulation for like for particles. So the first one is the linear spring dashpot model, or linear spring and damper model, and the Hertzmindlin no slip model. So the linear spring dashpot model is simple, and the reason why it's simple is because it's a linear model, and of course because it's linear, it's a less approximate value to the actual value that is actually occurring in the experiment or in the collision. And then the spring force is directly proportional to the overlap, and the dashpot is like proportional to the relative velocity. And this model actually allows like larger time step because of the simplicity, and of course it also like engenders like quick simulation, and then it's cheaper because you can run it faster. So but the Hertzmindlin no slip model is non-linear, and of course because of that it's complex, but because of the complexity and the non-linearity, it has much more accurate approximation to the actual value of the forces at the point of contact. So it's accurate, and then like the force calculation is much more efficient. The normal force, uh, it obeys the Hertzian contact theory, and the tangential force obeys the Mindlin-Deresiewicz model from 1979. And then the forces, we have like the damping coefficient is directly proportional to the coefficient of restitution, as we are going to see later, and the tangential force is limited by Coulomb friction. We're going to see that also later. So there are two methods, like the regular way that we get our frictional force, which is like coefficient of static or dynamic friction, and then the force, the normal force, and then there's some other there's some other method of calculating it that involves like the shear modulus, but like the value which is minimal, like the minimum value, the smaller value between those two is what we actually take to be our tangential force. Yeah, so this is the general workflow for doing hand calculations with steel ball, like at the most basic level, whether it be like two colliding steel balls or a single steel ball, like dropping from a height or like oblique direction. So first off, we pick our contact model. Can decide whether we want to use spring dashpot model or the Hertz-Mindlin contact model, and then we identify the key parameters, like some parameters like the mass of the balls, the radius, the material they are made from. That will help us pick the coefficient of restitution and the Poisson's ratio. And then next we will go to like calculate or estimate the effective parameters, so like the effective radius, effective masses, and effective mass, and then effective Young's modulus. And then we calculate the relative motion between the balls in a preset direction, and then we calculate the overlap also, and then we calculate the normal force. And then afterwards we calculate the tangential force, and finally we update the velocity. So if we were to do it like numerical, so after updating the velocity we go over again, but I'm going to skip the model selection because we already know the parameters. I think it's just the intricacies that is going to change, but like we just keep like iterating until like we get to what you want, or like in this case until or like in the case of like a ball like dropping from an height until it is like level, and then it's no longer like bouncing there's no rebound anymore. So over here we're going to go down into the hand calculations with the linear spring dashpot model, just as you have seen before. Two balls of masses m1 and m2 with velocities v1 and v2 respectively. We know the Young's modulus E1, we know the radius of the balls like R1, and then the Poisson ratio, the V, like that variable like V1, and on the other side for the second ball. So we did the parameters are the masses, the radius, and the velocity. So we know that like for this case, like as simple as possible, our balls are identical, which means they are of the same size, and of course the material is the same, and the material is made of steel. So our Young's modulus is 200 gigapascal, and the Poisson's ratio is 0.3, and our coefficient of restitution is 0.8. So like we already know we're going to use the linear spring dashpot model, and we're not looking at the tangential force, we're only looking at the normal direction only. Yeah. Given those values from the previous slide, we can calculate our effective mass, and it is 0.05 kilogram, and the effective radius at 0.005 meters, and the effective Young's modulus, which is 1.10 times 110 gigapascal, or 1.10 times 10 is per 11 pascal. And then the derivative motion, like derivative velocity, and then overlap. So we know that, well, if we're going to say overall, we want to look at the resultant like motion. We want to look at the positive direction being the direction that ball 1 is going. We say like the velocity of ball 1 minus the velocity of ball 2. And of course, if we take as our own convention for this case, if we take the velocity of v1 to be positive, obviously the velocity of v2 has to be negative because it's going in the opposite direction, and velocities are actual vectors. They are not scalar quantities. So we have a relative velocity as 2 meters per second, and also if we must calculate the maximum if we must calculate the maximum that displacement, we have to like equate, do energy balance and equate these two formulas that we're seeing over here, and from there we can get our maximum displacement as as in the overlap, which is my maximum displacement E at the point of contact, how far they can go, if they're going to overlap or if they're just going to make contact and then like split apart, or like be elastic and go apart. So it's 13.9 microns. Afterwards, we will calculate our normal force. But before we get the normal force, we need to get the value of the normal stiffness. So, and the normal stiffness is really is given by this relation 4/3, then effective Young's modulus, and then square root of effective radius, and the value is 1.04 times 10 raised power 10 Newton per meter. And then we also did the calculation of our damping coefficient, like C sub n, as this relationship, and we got the value as 3,219 Newton second per meter. So like overall, because we had said earlier that we only want to look at the normal force and want to look in the normal direction, we don't want to consider the tangential forces. So we have our the maximum contact force as 1.44 times 10 raised power 5 Newton. And these are the velocities after collision. So today is probably is majorly a function of the coefficient of excitation. It's like saying 0.8 times the velocities in either direction, like as we have earlier. And from our analytical method of doing this, like is actually logical from the Newton's first law, Newton's second law of motion. Yeah, so these are the velocity of the ball 1 and the ball 2 after the contact and when they go apart. Yeah, so now we want to do the exact same thing, but without using the linear spring dashpot model. We want to use the Earth-Mindling no-slip model now. So we have, just as before, we have like two balls going in different, like in opposite direction. I mean, like approaching each other from different direction with velocities v1 and v2 and masses m1 and m2. We know they have their own Young's modulus. They have their own individual. Oh, well, they are similar because we are still going to like maintain the identical ball. So we have the same radius and the same Poisson's ratio. So we know the key parameters over here. The Poisson ratio is still 0.3. Young's modulus is 200 gigapascal. The coefficient of excitation is still 0.8, and the coefficient of friction, like either static or dynamic, is still 0.3. And we already know we are going to use the Earth-Mindling no-slip contact model. Yep. So just like we did before, we're going to calculate the effective parameters, which includes like the effective mass, just like before, 0.05 kilogram, the effective radius, 0.005 meter, the effective Young's modulus, like just like before, we have like 109.89 gigapascal, and the effective shear modulus, because we're going to need the effective shear modulus value when we're calculating tangential stiffness, and of course eventually tangential force with the Mindling model later on. So we have it as 45.25 gigapascal, and then we have derivative motion and overlap calculation. Just like before, we have 2 meters per second, and the maximum overlap with this relation we have like 72 micron. Yeah, so we calculated the maximum normal force with this relationship 4/3, then effective Young's modulus and square root of effective radius, and then like the square root of the third power of the maximum overlap. So we add like 6,380 Newton, and then we calculated the tangential stiffness like from the shear modulus that we got earlier. So we have the value at 1.28 times 10 to the power 9 Newton per meter, and then finally we calculated the tangential force, which is the minimal value. I mean, like the smaller value from between the regular way that we calculate our for frictional force, that like coefficient of static or dynamic friction, and then the normal force, between that value and the value that we're going to get from the multiplication of the tangential stiffness and the tangential the tangential overlap. So the minimal value was the one from like friction, and it was 1,914 Newton compared to the 92,160 Newton that we got from the other one. I mean, because it is Coulomb's law limiting, so we have to go for the lower value. And just like before, So yeah, finally, just like before, we have the AND calculation, still with the Eichmann no slip model, and we still have our velocities V1 and V2 after the contacts as negative 0.18 meters per second, because it's going in the opposite direction to our original convention for the velocity. So originally, if we were going, if the ball that was going right was the one in positive velocity direction because it's a vector, I know that was going left was the negative one. But after meeting, momentum is obviously conserved, and then like the goal is an elastic collision. They go in opposite direction. So the v1 that was the ball one that was approaching, that was moving towards the right before, is now going towards the left, and it's now like taking up the negative velocity, which makes a lot of sense. And the ball two that was approaching in the negative direction is now going in the positive direction, in the right direction, and it's now 0.8 positive value. And that is all for it, the AND calculations.
Thank you for my partners to introduce the method of the discrete element method. This part I will introduce some numerical examples of the DEM method. I will introduce it into 5 parts. The first one, I will introduce the problem we want to solve. And next part, we will see the model and the parameters. And the third one, I will just tell you what is the method we used. And next, we can solve some results of the numerical examples. And at last, we have 2 questions to test your understandings. First, I will introduce the problem we faced. The first one is the application scenario. When we drill a well, it may be several hundred or thousands meters, and in these steps there are many fractures near the well. We can see from the first figure that many fractures is near the well, and we can also see from the second figure that there are some fracture leakage. And in the third figure, we can see that the fluid is clearly, we can see it leak from the leak into the fractures. So we built the model in the fourth figure. We use the fracture model to simulate the fracture lost. 2 wedge-shaped models will be used to simulate the fracture, and the large fracture wideness of the inlet is 6 millimeters, and the outlet is 2 millimeters. And in the smaller model, the fracture wideness of the inlet is 3 millimeters, and the outlet is 1 millimeters. We can also see from the top and side view of the fracture model to see the size of them. We can use a mathematical equation to give a validation of the results of the velocity of the fluid and the particles. And the second part, we lift some parameters used in the model. This part I will introduce the method used, which is computational fluid dynamics and the discrete element method. Thank you to my partners who introduced the method before. Now I will focus on the method used in the software, which is the STAR CCM. So there are 3 mechanical mechanisms. First one is that the translational and rotational motion of the fibers is governed by the Newton's second law, and including the effects of the fluid drag contact forces and gravity. And the second one is that the drag force is exerted by the fluid on the fibers, calculated by the DEM model. And third one is the interfigure contact forces. It's using a spring dashpot approach. And we can also see the mathematical equations as listed. The method we use is the CFD and DEM coupling technique. So it is between the fluid and fiber phases during the simulation process, which we can see from the figure. It shows that it is a dual time step strategy. So the CFD method has a larger time step, and the DEM resolves in interactions with smaller sub-time steps. And the second one is that the simulation has the data exchange during the process and allowing for continuous feedback between the fluid flow and particle dynamics. And third one is compared to one-way coupling. In this method, exchange enhance the accuracy in capturing multi-phase interactions. This part I will introduce the first numerical example. We can see from the figure that after about 42,000 time steps, the fibers build a structure, a bridge-like structure, and can seal the fracture. We can also see from the second figure, which is the mass flow rate monitor plot, which represent the mass flow rate of the fluid from the outlet of the fracture. So it reduced to zero quickly, which means that the fluid cannot pass the outlet. So the sealing happens successfully. The first numerical example is from a journal paper, and this example is the one I rerun it and still in the StarSysM. We can find that in this example, the mass flow rate also comes to zero at last. But it may take longer time than the first one. The reason of that may be some fibers pass through the voids between the bridging before it is finally plugged, so it takes more time. But it is also successfully plugged at last because the mass flow rate of the fluid come to zero. In this part, I want to test your understanding of the method. So the first one is which model was used to calculate the fluid drag on fibers in the DEM simulation. And the second one is in the coupled CFD DEM simulation, what strategy is used for time stapling? So the answer of the first question is C, the third one, which is the Defalice model. And the solution of the second one is B, the second one, which is the door time step strategy.
Regarding its application, the discrete element method, or DEM, has been widely considered suitable for simulating problems across various fields. Before the development of DEM, other methods such as finite element method or FEM treated objects as continuous media. However, in many applications, materials are inherently discrete, composed of particles, grains, or fractures. To address this, DEM was developed as a method that implements Newton's laws of motion and models the interaction between particles based on force and relative displacement. Today, DEM is used in a wide range of disciplines, including earth sciences, civil engineering, and agricultural studies. In earth science studies, DEM has become popular for modeling faults and fractures. In one study, DEM successfully modeled the influence of basement infill faults on the geometry of overlying sediments or rock formations, as shown in the time series figures on the right. The model accounts for the three principal stresses, including tectonic and gravitational forces, and reproduces features such as hanging wall synclines, which are commonly observed in geological outcrops. The model also shows that the Treasure model effectively represents the kinematic behavior in this type of tectonic setting. Another study demonstrates how DEM can simulate the development of faults and fractures in a segmented fault zone, as shown in the figures on the right. In this model, the main faults are represented by red particles, while the linking faults or fractures are shown in blue. We can also observe the formation of damaged zones near the main faults in the later stages of the simulation. The goal of this modeling is to predict the timing of fault reactivation and the peak shear stress using DEM simulation. The simulation involves robust calibration of the microparameters of particles, allowing the model to replicate the mechanical behavior of natural rocks. For example, during the simulation, particle bonds may break if the applied forces exceed the Coulomb criterion, which is defined by the cohesion and frictional properties of the material. Another application of DEM in earth science and engineering is hydraulic fracturing modeling. Hydraulic fracturing involves injecting fluid to enhance the permeability of subsurface rock formations. This method is used in various fields, such as enhanced geothermal systems and waste disposal in basaltic formations. The figure on the bottom left shows a simplified illustration of how a hydraulic fracture network improves permeability or conductivity, allowing fluid to flow efficiently from the injection well to the production well. Since DEM uses discrete particles to represent geomaterials, it is particularly suited to simulate fracture networks. However, to solve more complex problems, a coupled approach combining continuum and discontinuum modeling is often required. This led to the development of the finite discrete element method or FDEM. By applying this coupled method, additional processes such as fluid injection, heat transfer, and thermal strain can also be considered. Other coupling approaches have also been developed, including DEM to LBM or Lattice-Boltzmann method and DEM to BEM or boundary element method. The figure on the bottom right shows a simulation of fractures induced around an injection well using FDEM. DEM and FDEM are also commonly used to simulate proppant injection during hydraulic fracturing in energy-related applications. As shown in the figure on the bottom left, proppant is used to maintain the permeability of rock formations that are previously fractured by hydraulic stimulation. The figure on the right shows a study using DEM to simulate how different proppant size distributions affect fracture permeability and conductivity. One of the key findings of the study is that models using uniformly sized particles, for example well-sorted propans, achieve higher conductivity compared to those using poorly sorted propans with a wide range of size. Lastly, here are several other examples of DEM applications in various fields. The figure on the left shows DEM used to simulate slope stability, which can assist in risk assessment for civil engineering. The middle figure illustrates a DEM simulation of powder formulation using dye filling. Meanwhile, the figure on the right shows how DEM can be applied to simulate the mixing process in the pharmaceutical industry.
In summary, the discrete element method is a numerical framework for simulating the physics of particle-based systems. It is grounded in Newtonian mechanics and incorporates realistic contact models to represent how particles collide, slide, and dissipate energy. Unlike continuum approaches, DEM excels at capturing localized discontinuities, making it invaluable for modeling complex phenomena such as fracture propagation, granular mixing, and particulate transport. From force mechanics and slope stability to propellant transport in hydraulic fracturing, DEM has proven essential in fields where micromechanical behavior matters. While it remains computationally intensive, the method's fidelity and flexibility justifies its use, especially as hybrid and coupled models continue to emerge.